is that this language is a wonderful combination of being object-oriented and functional at the same time. While this feels really good to hear this, actually all the features come at a price. So by using the Scala, you're able to write a simple code which hides away from you how it's actually implemented and all its inefficiencies. I can give you several examples of those inefficiencies. The first one will be boxing. So let's say you have an array and you call a sum on it. Array of integers, just a normal array, which contains 1, 2, and 3. The first thing that's going to happen is this array is going to be converted to a wrapped array without you knowing. And then actual operations are implemented in the indexed sequence. The actual implementation of the sum will take a numeric because it abstracts over what's actual underlying type. You could be summing integers, you could be summing something which has non-trivial operation of addition. And it implements it in terms of fold left. And then fold left itself is implemented in terms of a tail recursive method called fold L, which is private in this class. The problem here is that by the moment you actually apply the original operation, which is summing for the integers, you abstracted over it multiple times. You don't remember that those were integers in the first place because you abstracted over the type parameter. And here, in order to apply the operation in a uniform way for all the primitive types and all the object types, the actual integers will be boxed. In case of summing of the integers, the slowdown that you'll have here is 13 times more than the actual operation that you're doing. So summing an arrays of integers in Scala currently is pretty inefficient because we spend most of the time just paying the price for a convenient language. You could say that we actually have a thing that should solve this problem. It's called specialize. So what you can try to do is you can put a specialized annotation on the type parameter of the wrapped array and of the indexed sequence. And then they say that it will generate specific methods which target specific types of the primitives and nothing else. Unfortunately, it doesn't work in this case. The main reason that specialization does not play well at all with subtyping. And here, obviously, you don't want all the operations to be copied in all the collections. They're implemented in some base traces, like indexed sequence. An actual wrapped array, which wraps integers and is specialized for integers, will not be inheriting from the indexed sequence, which is specialized for integers. It will only inherit from a generic one. So you'll still box. The other problem with specialization is that if you want to specialize, you're required to specialize all the type parameters. So let's say we want to write a function which additionally to summing integers logs intermediate results. Then you'll have additional parameter which actually represents a logger which could log those integers. The problem is that specialization is not at all able to express this thing because you have only one type parameter specialized but not the other. There's actually a project around that tells that it had solved this problem. It's a Miniboxing by Vlad Urete. And yes, if we speak about those two problems, it actually did. But there is an additional problem which is common to both of those two projects. Let's say we want to specialize a function 3. Function 3 has 4 type parameters. Scala has 10 primitive types. How many specializations are needed here? If you use specialization, that it means that for every type parameter you need 10 implementations. You have 10,000 classes. If you use Miniboxing, it needs 3 implementations for every type parameter, so you'll need only 81 class. But I would actually ask a different question. Are those all specializations actually needed? I mean, potentially yes, but are they needed in your program? So in your program, if you're actually able to use all the potential combinations of the type parameters of function 4 or function 3, it means that you have at least 10,000 places where you call a function. This is not a real program. So in real programs, you don't need all the specialized combinations. You need some of them. So what if we could actually generate only the ones that your program relies on, only the ones that it used, and throw away the ones that are not needed? The question boils down to how do we detect which ones are used by your program. So, and the answer starts from the tasty. I guess you already heard this name if you visited Martin's talk. To boil down, that's tasty is a replacement for Scala signatures. Not only it includes the top-level signatures, but actually it includes the full source of every class and function compiled by Dotty. It means that we actually can know how the library, the standard library is implemented, or the other library which is shipped from Maven. And we can inspect how it uses the arguments, what's the control flow of it, and how it uses type parameters. The type parameters is the main thing here. We want to know the abstract type parameter, which is, for example, defined in this fold left or fold out. What are the actual instantiations that happen in your program? And the answer here is the call graph analysis, or more precisely, type flow analysis based on the call graph. So we start by defining some entry points of the program. This could be either the main method of the program or something that you explicitly annotated because you're going to use some non-trivial way of calling it, let's say Java reflection or Scala reflection. Or that's a library that's a function that you assume will be called from native code or whatever. So we start by marking these methods as initial methods for our type flow. And from these methods, we see how type parameters are instantiated and propagated. We track how they flow through methods which are already called, and we also track which trait combinations are instantiated. You can say why traits are special here. The problem is when you compile or optimize a method defined in a trait, you don't know what are the other methods of this class. Because this trait can be combined with everything, you cannot assume anything about the methods in the traits. It actually means that there is no way you can ever optimize a method in a trait because you know nothing about where it actually would be. Unlike in classes where you actually at least know the superclasses and linearization order gives you answers to all the questions. So there is a paper about how it's done in Dotty. That's a paper by Andrei Lotak, Constructing Call Graphs of Scala Programs. And the main takeaway message there is that if you use something like ProGuard or something like that works in the Java bytecode, you already lost most of the information. If you'll be doing this on erased types after mixing, traits will look like they're called from everywhere, literally. So all the functions will look the same because all of them are just implementation of a single trait. So let's have a look on this example and see how in this particular example the type flow will work. So here we have a main method, which is an entry point of this program, which prints in some of the integer value of the arguments of the program. So here we can see that here we have a map method. This map method actually gets a type parameter, or here we have a sum method. Let's concentrate on sum. We can see that it actually gets a type parameter which is an integer because the underlying collection is integer. We mark sum as being called with type parameter integer, and then we iterate over sum. And we see that fold left here is called with the same type parameter as sum is, this b. And we can iterate over fold left and see that the fold left here is also called with integer. We do the same with fold out, and only then we actually get to this place where we can see that the abstract type, which is from b, a to b, is actually instantiated to a single type, integer, integer, integer. So for this particular program, you know that there is only a single type of function that could ever be in this program. You don't need all the other specializations. So I won't go into details of how other things are implemented. I just want to name a few that Linker could do using the similar strategies. The first one is this smart specialization. We don't want to specialize for everything. We don't want to specialize for things that don't happen in your particular program. We want to tune the libraries that you depend on to fit perfectly only to your particular program. The next one is that code elimination. As I told you, traits and erased signatures after erasure look like they're called from everywhere. You don't know which type parameters are there because they're erased. You don't know which trait combinations are instantiated. If instead you do it on the high-level representation, you get a lot more precision. For example, for Squirrel, the database mapping engine, if you use ProGuard, which is the main tool to do it on Java, using bytecode, it will be able to see that there are 1,500 alive methods in this program. But actually, there are only 400. All others are false positives. And if you try to optimize for them, you'll be once again optimizing for things that don't happen. The other thing that you can do is you can convert classes to value classes. I'll talk about this in more detail in the next slide. The other thing that you can do is you can infer more precise types. For example, in the previous program, we've seen that we have a map defined, which is called on the array of strings. Actual map is defined on the indexed sequence. Inside indexed sequence, you assume that this type is indexed sequence. But actually, the only type which map gets ever called is array. So you can safely change the types while being still safe, but while being still sound, and give all the variables, all the functions, everything in your program, types which are not as static as they were previously. Those are the types that program will still type check with. But those are the types which actually happen. This allows you a lot of optimization opportunities once again. The other thing is eliminating virtual dispatch. That also has a lot to do with inferring more precise types, and I will talk about it separately in the next several slides. The next one, after you've done all of this, you have a lot more knowledge about your program. You can see that some stuff was marked as a variable originally because there was some method that would, in some case, mutate it. But now you know that this method is dead code. It's never used. You can as well mark this var as a val. And then the compiler itself will use more efficient encoding for it. And the next one, after you have a lot of vals everywhere, which previously maybe used to be vars, you're likely to have a lot of duplication. Because somebody copied a val just to mutate it and iterate over it. And because they're duplicated, you can just remove them. And this means, for example, you start removing fields. If you see that all of the fields of some particular class are always instantiated in the same value, it means that this value goes copied through several layers of vals, and then it reaches this class. You can as well remove this field and inline the value everywhere. Okay, so talking about the smart dead code elimination. Here are several programs that I've tried to compile, see how many methods are there originally, how many methods are there after ProGuard minimized the program, and how many methods are there after linker minimized it. So I've been already talking about Squirrel, which is this database mapping thing. Kiama is a natural language processing library. It's enormous. It's huge because it tries to be able to handle whatever language do you have and be able to statically decide everything about it. It has enormous amount of traits because it tries to be extendable. That's how you do extendable stuff in Scala. You make traits. And then because of this, if you analyze it on the already lowered representation of the class files, you're once again very imprecise. The last example is Dotty itself. So the Dotty itself currently contains 35,000 methods. Actually, that's an interesting thing because if you listen to Martin's presentation carefully, he told that the project he's working on, and that's Dotty, has only 100 lines. The interesting thing here is that compiler actually creates a lot of functions because it needs to encode your code, which is small and easy to write, in the notions which are basic to the language and to the platform. There are a lot of functions created around which you don't see. For example, every time you call a map, there is anonymous functions being created inside, which could be either anonymous class or really an anonymous functions, a lambda in Java 8, but still you pay a price for it. By using a linker, which is smart enough to start removing those things, which is smart enough to start removing lambdas, inlining classes, making value classes out of normal classes, you can actually lower this number to the factor of 2. Using the ProGuard in this case once again shows that it really is able to remove the methods which shouldn't be in there in the first place because those classes are just not used by the compiler itself. There's some kind of legacy that's been lying around for some time. Okay, so I've gave you a teaser about converting classes to value classes. In case you don't know what a value class is, a value class is an abstraction which is present during compilation and the compiler tries hard to eliminate it. So the value class is something which wraps a single field and the compiler tries hard to remove the wrapper and just represent it as an underlying field. Let's say you want the notion of meters. which is backed by an integer inside. You don't want to box this meter as a box which has an integer. You would better prefer the compiler to be able to actually represent it as an integer but perform operations on it as it was meter. So for a value class, for a class to be a value class, it needs to follow some restrictions. The first restriction is that value classes aren't inheriting from any ref. If you have a class which you synchronize over, then this could not be a value class because there is no synchronized method on any val. So because we've made a call graph, for every class, we know which methods are ever called on it. We know that some classes, like the particular class meter, which reasonable program will ever synchronize on meter. Yeah. So the other restriction is that it needs not to have side effects in the constructor. This reason comes from the fact that actually compiler sometimes fails to have this underlying representation and will need to box it back. If the construction has a side effect, it means that while boxing and unboxing several times, the side effect will be repeated. So that's why this restriction is here. And the other restriction is that in normal value classes in Scala, they are final. In my cases, I say that they should be effectively final. And by effectively final, I mean that there is no non-dat code classes which extend those. And here, the question of effectively boils down to the moment when you compile. So the question is, when I close the world, I do some assumptions about the program. And if this program itself is a library and somebody depends on it, some of my assumptions could be wrong. And Tasty, once again, comes here with a full help. When I actually compile the end program, that's the moment when I will optimize the library, because I'm tuning the library for the program. I'm also tuning the libraries that this library depends on. I have the source for all the transitive dependencies. If I don't have the source code, then I cannot optimize it. I'll just boil down and do the very conservative assumptions about it. So while doing these assumptions, I actually break binary compatibility, because I remove some methods, I remove some classes, I get the signatures which were more precise than the original ones. And for example, originally a method took some object, but I was actually able to infer that this object is always a meter, and then I made the meter be an unboxed integer. And then you have a signature which is not the same from the Java point of view. Original method took take a reference, and this one takes a primitive. So binary compatibility here is lost. It means that, for example, if in your production you're used to just, if you want to update the library you depend on, you just update it on the class path, it's not going to work. Because actually your program doesn't depend on the library anymore. I encoded for whole the library in your program. Instead, I provide the source and Tasty compatibility. Source compatibility is the one that Scala gives you. Tasty compatibility means that in runtime, I'm going to check that the dependencies that you have are still the ones against which I did assumptions. Actual Tasty always contains a snapshot, the unique identifier that represents this particular file. And if in runtime you have a library which is of a different version, or just of a different build, I'm going to either give you an error, or if you wish, I will recompile there. This effectively means that there is a whole new way of deploying programs. You just put in the libraries, and you configure the environment so that those libraries will be read in runtime, and then will be optimized in runtime. This will be slow, but then it will run fast. Okay, so the other thing that I was talking about is eliminating virtual dispatch. There's one commonly used strategy for eliminating virtual dispatch, and that's inlining. Let me illustrate it. To be clear, it's not the one that I'm using. I'll present mine in the next slide. So let's say we have this array of 1 to 3, and we call sum on it. We know that this array is a specific type, and so we can actually know which sum is called. We can inline the very source of the sum in this line. That's how it could be performed. So we inline the source of fold left, replacing all the calls to the argument with the actual value of the argument. And then we've did several rounds. So we've inlined fold left, we've inlined fold out. Now we have a problem. Fold out is recursive. It means that if you'll start inlining it, you'll never finish. So you need to boil out. The problem is that by now, you've eliminated several virtual dispatches. but you didn't eliminate the main one, which takes most of the time. You've eliminated the one that the GVM actually will be able to do on its own. So you've just made the source bigger. You made the compiled classes bigger for no good reason. What I do instead, okay, so the other thing that's if you inline, you could be inlining the very same method several times in the very similar contexts. Then you'll actually be increasing the size of your program. And there are interesting counterexamples. You can have a pretty small program, which if inlining is not stopped, will grow exponentially, even without recursion. The way how it's solved in most inliners is that they have some limit on the method size. And if the target method is big enough, they will stop inlining. That's heuristic, which just works in practice, but has no good reasoning behind it. The other thing that's when you inline methods, you can actually create huge methods. And most VMs, like the GVM, is not that glad to optimize huge methods. One of the heuristics used inside the GVM itself is how many variables you have there in the method. If you have more than 255 variables, which fits in a byte, GVM will quickly boil out and not optimize your method at all. You'll be staying in interpreter or C1 compiler. You'll never get to C2. And the other thing that's most of what inlining could actually do would be actually performed by the GVM or JavaScript's VM at all, on its own. And it will actually use runtime types and do it better. What instead I don't do inlining, I do cloning. So I see in which context this method sum is called. So in this particular case that we had there, it was called with a specific underlying type, which is integer, and which led to specific underlying type of numeric, which is integral. And because now in Scala and Dotty we have singleton types, we can actually express in types the fact that it's this particular clone of the method is always called with the same argument. And that's what we do. We say that the type of the num is instance integral. We do the same with fold left. So the fold left itself, it's called with the 0, which is a singleton of the specific instance. And that's the compiler will actually able to know that this singleton has only a single value, which is int 0. And it's called with a specific function underline, which is addition from, once again, the singleton type. And we can do the same even with recursive methods. There's nothing wrong with recursive methods having singleton types as arguments. So the advantage is here is that if you use the same method and you'll sum integers in any other place of your program, you already have the clone of this method which fits this place perfectly. And then, because the analysis is not limited to the single methods, it's interprocedural, then this doesn't stop other optimization from being applicable, because all the knowledge is still gathered. If the method is worth inlining, either GVM or JavaScript will be able to do it on its own, for its own reasons. But you've already done specialization for the actual arguments that you have. So the advantage here is that it indeed handles the recursive methods. It doesn't give you a big increase of size because the arguments are actually going to be removed because they're always the same value. And you're going to reuse the clones that you had. And if you're not calling the generic method anymore, it will be that code eliminated. So in your case, if you had, in this particular program, if you're calling some only arrays of integers, it will create a clone which fills it more specifically, and it will remove the generic method. We have no huge methods. We don't do inlining. Methods only decrease in size because the arguments are removed. And the biggest advantage here is that this isn't something new. This is the same mechanism that does specializations. But instead, we specialize for singleton types, not for primitive types. So we don't need to reinvent the wheel. We already have everything here. OK, so let me demonstrate you a bit of how it works in practice. OK, so here I have some class here, which is a similar structure of what Dotty continuous integration has. So you have a build. which represents a version of Dotty that's been compiled and tested against the tests to see if it actually follows the test or this build, the committer should improve his own code. So we would say that the tests following the Unix principle, they return an exit code. An exit code of 0 means success. Everything else means some kind of failure which is specific to the particular test. We don't know what it means. So the test here is something that takes a build and returns you an exit code, which means whether the test has failed or succeeded. Okay, so now we have a test suite. Test suite is something which takes plenty of tests and it can run those tests on a build. And it does it simply. It just maps all tests, testing using every test to get an exit code from this particular build. Then looks for some code which is a failure. And if there is no failures, it will return 0. Otherwise, it will return the failure code, which was the first one. That's how, let's say, most of the engines are implemented. The similar code you'll find in Jenkins. And now you have the main method, which actually does build and runs the test suite. Okay, so let's see how this method, this class does actually look like. So I should have a bigger terminal somewhere here. Sorry. Okay. So so I have a command called linker, and we'll compile this .eci.scala. If you don't give it any arguments, that's just normal compilation as in the .c. If then we will call java-p on the .eci $, because that's an object that's actually encoding, you'll see that here we have plenty of methods. But if we'll ask it to give you static ones, private ones, okay, I'll just use debugger, which will be simpler. So that's how this code actually looks like. That's a decompiled code, which is equivalent Java code. So you have plenty of methods here. As I told you, the compiler will silently create them. The ones for mapping, the ones for finding. At all, you'll have 17 anonymous functions being represented for this class, which was a small one. So if instead we use linker to compile it, then we have several optimizations level that we can apply. The first one, and we also have the all parameter, which will apply all of them. And currently I have a custom build which tells what will happen. So it printed quite a lot of what it did. But let me show you several examples. First of all, it's seen that the exit code that we had there and the test suite as whole, nobody synchronized over them. And they actually had a single value as underlined. They became value classes. Linker removed these classes entirely from the code. Then it's seen that we have a lot of aliases being flying around, the variables that the compiler created, the variables which were in the original code, and it started removing them. So we can see here that it starts removing aliases in the standard library, which you use, and then it starts to remove the pattern matching which it generated on its own. So for every class, you have still the hash code. For every value class, you still have a hash code and the toString generated, and they have a pattern inside. Most patterns, the way how they're compiled, are not that efficient, and you have a lot of variables which are just copied around. And the optimizer was able to remove it. So every time you see this selector, it means that there was some pattern match inside which was just copying a variable. So in the end, it started to actually remove methods. So let me show you. Here. So it started removing parts of the standard library because you don't need them. It started removing parts of predef It started removing variables that you've just defined but didn't use the result. It kept the side effect of computing these variables, but it removed the use of register to store it, because you will never use it. Those f's that you see here are actually results of inlining the map function and filter function. Those were the arguments of clones of those functions, and it's seen that they are always aliases. It's removed them as alias. It's removed their uses to the usage of what they're alias to, and then it's removed their arguments. So that's why you have those. Then you have a lot of anonymous classes and anonymous functions which are not used. And in the very end here, you have pre-def being removed. It means that everything that you used from Scala literally is in your program. The standard library disappeared as whole. So original members means how many methods were there in classes that could potentially be instantiated by your program. So when compiler compiles your program, it reaches all the classes that you actually use on the bytecode level. So all those classes originally had 1,000 methods. By using all those optimizations, we were able to reduce number of methods to 99. Okay, so just to show how this code actually looks like, in the end, that's how it looks like. So you have this main method, and you have this calls to compile build, and here you create this array of functions, which will actually be the test that used to be the test suite. Now you have this wrapped array. This actual wrapped array is something that you iterated over in the test suite itself. And you were creating this array of exit codes as a result of execution. Previously, you had a lambda, you had a lot of virtual dispatches. Here, instead, you have just a for cycle. Actually, these variables are just the one that the decompiler was able to synthesize names for. So here, it's just the one that goes past here, the one goes past here, the one goes past here. Actually, here, we have 4 bytecode instructions inside the cycle, aside from the cycle iteration itself. Then you have this array being created. One other thing that I forgot to mention, that though you see here wrapped array of ref, it was able to infer that this actual ref is not a ref. It's always an exit code that kind of used to be a reference, but it's not anymore. It's a value class now. So when adding an element here, you don't see any boxing, because you're actually creating an array of integers. Now you have this wrapped array. And the only kind of wrapped array that we have in this program is our array of integers. It's not seen here because that's the only one. And now you iterate over those, trying to find something which used to be a failed test. But because we have several cycles of inlining methods which were called only once, then we have it. The cycle here is simple. We're not calling the failed method. We're not boxing object. We're not doing anything. We're just looking for the first 0 in this array. It's enormously fast. And now that's what happens with the getting of the exit code. So that's a point which, if you came early to this talk, I was telling Lucas that I'm fighting his optimizer. The problem is that I actually have a single task which always fails. And this can be seen statically. Currently in Gen B code, which is shared backend, Lucas is working on optimizations that work on the bytecode level. The problem is that after cooperations of the both optimizers, it's actually able to infer that the test will always fail. And because of this, the static type of this variable, that it looks like, or that the test will always succeed. And it's able to always infer that the static type of the return value is none. There will be no failures. So given that, if we had actually partial evaluation, this itself could be evaluated to exit code of 0. But unfortunately, evaluation is a separate, very hard topic, and this linker doesn't contain it. Yeah. So just to wrap up on what happened here. So I actually measured how does this class work in runtime. So, but the measurements I did a bit earlier before I improved the code elimination. So actually the numbers here would be a bit better. The problem with getting these numbers requires custom build of the GVM to actually go to the GVM code side thingy. Because you need to make a debug build, because normal GVM doesn't track this. So yeah, so for this particular program, including all the methods which were there in the library, which were there loaded by the GVM, we had 1,000 methods in the original code. If we run ProGuard over this program, including the standard library, we'll have around 800 methods. And in linker, we used to have 196, but now we have less than 100. So actually, the last table should be improved. So the bytecode size is the actual size, how much do the actual class files take in the file system level. So the original code was 0.5 MB. And by saying 0.5 MB, I actually stripped by hand the standard library, because otherwise the standard library itself is 8 MB. So it wouldn't be fair comparison. So the ProGuard was able to do it on its own, stripped big parts of the standard library, but not all of them. And it wasn't able to remove some of the methods that were there. Linker did a better job on this. The next line is, after you've run this program 1,000 times, the state of the inner data structures of the GVM. GVM contains some caches which have the compiled code inside. And the more code you have, the less time GVM will spend optimizing every particular function of your program, because it tries not to spend much time on optimization, because it actually wants to run your program. So the less code you have, the more time C2 and various level of optimizers in the GVM will be spending on the real code. So in this case, the other thing that's the code here and the code loading on the GVM is performed per method. So those numbers actually represent the size of live methods. By using a linker, the live methods, which were originally around 2 MB in the library, were able to be stripped down to become almost twice as small. Number of objects allocated is the similar instrumentation that you can do in the GVM level. You can track how many objects are allocated per those 1,000 runs. Effectively, how you do it, you disable the garbage collection and you use its reference counting to know how many were allocated. Original program had a lot of lambdas. It had a lot of anonymous classes being passed around. It had a lot of boxing. Interestingly enough, ProGuard was somehow able to improve this. I guess the main reason here that ProGuard somehow restructured the source that the GVM was able to do on-stack allocation better on its own. GVM is sometimes able to do it if it had good enough profiles in interpreter. It doesn't happen often, and that's the graph that showed us. Linker, instead, was able to prepare methods in the way that either there were less allocations or the methods were simple enough so the GVM was able to do stack allocation initially. So in the end, you had 4 times less objects being allocated here. So there are several futures ideas so the one that I presented are the ones that are currently being implemented in different stages of being ready for production. Or different situation of not being ready for production more precisely. So some other ideas that we're considering is the lazifying of lazy vals. Let's say you have a lazy val, and you can statically see which particular locations in the code does it actually get initialized. Then you can remove all the checking of these lazy vals and just replace the place where you actually know that it's initialized by the initialization code. By doing this, you remove synchronization that lazy vals incur, you remove fields that lazy vals create, and you'll generally make the program easier to optimize for upcoming optimizations, be it the GVM itself or other optimizations that you've implemented. The other thing that we consider is adapting your program to silently start allocating memory off heap. And I concentrate on this on the next slide. The other thing is the duplication of methods. So let's say how many, you have a lot of case classes in your programs in most cases. most of these case classes have a lot of methods being synthesized from them, like the builder method in the companion object, like equals, like hash code, several methods required for pattern matching and can equal. I think that all those methods in all the case classes look very similar, but they share no bytecode. You instead have a lot of methods that were just flying around, it's effectively copying each other. If instead we were able to see that some methods look very similar and can be actually extracted to a common method, this could improve the size of the caches of the GVM. That's actually optimization which should be performed carefully, because by doing this you can actually start creating virtual dispatches and megamorphic dispatches, because you're joining the code paths which were different previously. Okay, so, and the Scala off heap. That's a small example that we've played around with Dennis, who is implementer of Scala off heap. So in the first one, you have a small collection of integers that you iterate over. That's a range. So all this represents a single object. And you for each over it, actually. You create one more range. You map this range, and you create a string of whatever you had. They say that GVM is good in creating short-lived objects and that code eliminating them. Here, for all this code, we actually have around 100 elements being allocated, or more or less, I would say 300 more precisely. In the second one, those elements are actually, those objects are not allocated on the heap, but instead for every iteration of the cycle, you have a region being created, which has a fixed size of 4 kilobytes initially, which is huge, but still. And it just packs object there. No garbage collection performed there. Instead, when the iteration of the cycle ends, the whole region gets destroyed as whole. And this is 20 times faster than using garbage collection of GC. What it shows is that if the linker is able to see that some classes are instantiated in, let's say, cycles or iterations or whatever, and it can statically discover the place in which it guarantees that the object will become non-reachable and should be garbage collected, it could instead create a region which contains all those objects, and they will get destroyed as a whole. Yeah, so that's the trickiest idea that we had. Thank you for listening. And feel free to ask questions.
Have you kept the running time of the linker from becoming very long?
So the problem here is that because I actually need to analyze all the transitive dependencies, it could indeed take a long time. The thing that plays into my strength here is that I'm one of the creators of Tasty. And Tasty originally was planned to be not only used by Dotty compiler itself, but by other tools. You can create custom sections there. So I'm creating a custom section there. Scala Meta, which there will be a different talk later, creates a custom section. I pre-compute a lot of values. But by saying a lot, I actually pre-compute something that helps me compute a call graph. In talking about the size of my section, it's around 3% of the size of the original class file. And the Tasty itself is 1/4 of the class file. So by using those sections, I'm able to quickly compute a call graph, do simple that code elimination on it, and actually load the stuff that you use. It's not that precise that I will do later, because it doesn't take into account, for example, the type flow that I was talking about. But it's already good because, for example, you don't need to load parallel collections if you don't actually use them.
Oh, yeah, thanks.
How does it work? How does this work if you're implementing a library? Do users of your library have to recompile your library then? Or?
So when you're implementing the library, you just ship it as it is. Either compiled by linker or compiled by Dotty, doesn't matter. But then when the end user decides whether he wants to use a linker or not, that's a place when the optimization will happen. If you've compiled the library with a linker, the user won't need to actually recompute those call graphs because there will be a separate section. So it means that you need to ship a single artifact and everybody will be able to use it. You don't need to do anything as a library creator. That's the user who decides whether he wants an optimized version or not. By using linker, you have several disadvantages. I want to be clear about it. First of all, as I told, all the dependencies get encoded in your program. So you cannot just update the library that you depend on by replacing on the class paths that some people used to do in their deployment. The other thing is that I start restructuring program a lot. You won't have good experience with debugging it. So that's why I really follow our soundness and not completeness road, because I really want to not introduce new bugs. If you had a bug in your program, it's still there. If you didn't have a bug in your program, and hopefully I didn't have a bug, then it's not there. So currently the goal is to test on all the test suite of the Scala compiler itself. It means, which is test suite of the Dotty compiler itself. It means you're as likely to have bug which is not covered by the test suites in Scala compiler, and then it's not covered in my test suite. So we'll benefit each other. If I see a bug which is my bug, I also add it to Dotty compiler and potentially Scala compiler. Test suite.
Hi. One of the problems that usually haunt ProgArd is the inability to identify classes that are manipulated or created by reflection. Is there anything with the tasty information? Is there anything that can be done by linker in order to identify those classes or optimize according to that?
So one thing that is not currently done, but could be done. So in Scala, you have such thing as structural types. And you can use structural types as a way to actually use reflection without knowing this. And then ProgArd will have really bad story in implementing this. What I can do instead is I can see which structural type do you actually have in your program, which actual structural types do you use, and make those interfaces. So if you have something, if you've been using a structural type which has a method foo, which returns an integer and has no arguments, I can retrospectively see all classes which define a method foo and make them implement specific interface. Then I won't need to go through the reflection anymore, and there will be no reflection calls. So from this point, indeed, by not using taste itself, but using the additional knowledge collected by linker, you can make a better story from ProgArd, but I guess if you're already using linker, I haven't seen ProgArd actually improve something. It actually was able to, let's say, you can use ProgArd if you want to obfuscate your code. Linker is not doing this. It actually, I would say it actually improves readability because it removes everything flying around which is not actually used. Yeah, but so yeah, but speaking about how I, on my own, handle reflection, all the calls which should be reflective calls should be explicitly annotated. So if you call a method foo using reflection, if I see this method is not an entry point and not called, I will remove it. Even if I see if this method is not an entry point by use from somewhere, I can optimize this method in the way which assumes the place where it was called. So if you want to use something with reflection, you need to put a specific annotation on this method. I actually give you a candy for it. So in Scala, you cannot rely on the name of the method when you call it using reflection, because it can be moved around, it could be name mangled or whatever. My annotation actually takes an argument, the name. And you can give it the name, and I will guarantee that that's the name that you should look through in reflection. Yeah.
Is there also an option to be safer when doing the linker optimizations?
So when I was showing the LTO here, I intentionally showed the LTO all. But you can actually opt in and run only some optimizations by hand. So all the optimizations are hidden by flags, like in GCC. So the LTO stands for link type optimization. Then you have several flags which enable or disable. So you can disable this dedup, which removes duplicated vowels, and then you'll have better experience in debugging. because something that you'll be looking will still be there.
Yep. Maybe I should finish my question. So, is there an option to only do the safe optimizations in the sense that they don't remove code that looks dead but might just not be annotated correctly?
So there is this DCE flag. You just don't support. You just don't add it. You don't use all. Instead, you say which flags you're interested in. So if you don't use DCE, that literally you'll have the whole library around it, and you'll have some clones which are tuned for your use case, but you'll still have all the generic methods around.
So would that be enough to make it completely safe then?
I guess so. So the only difference is that some classes, for example, using the value class thing, actually disappear. So value classes originally don't have good story with regards to Java reflection, and that's, I guess you also need to disable this.
All right.
Yeah.
Thanks.
It's also a question about debugging. It's about exception stack. Is there any tools that allow me to understand where the exception is happened from the application log?
So
yes,
if I got your question right, you want to be able to get the original stack trace.
Yeah, of course.
So currently I'm not doing this, but potentially I can emit something which is very similar to the JavaScript source map. And there could be a separate tool that actually takes the stack trace which you have here and maps it. The thing is that it's likely that this tool is not specific to linker at all, because we already have metaprogramming in Scala macros, and you don't get good exception there. So we have a lot of things which aren't actually expressible in the notions of the positions that the bytecode has. For example, when you compile a class file, you cannot say that those instructions aren't actually from this class, they're inlines from somewhere. And it means that, for example, even in the JSM, if you have at inline annotation somewhere, and you throw exception in the method being inline, you'll have a wrong stack trace. So yeah, I guess it looks like our ecosystem will need such tool at some moment.
So thank you for your work. When is it available? And can we use it?
So currently, because the Dotty internals itself are not settled, the project changes fast because it needs to adapt to the current state of Dotty. For example, the implementation of mixin changed a week ago, and I needed to actually change how linker works to be in accordance with the old mixin comparing to the new mixin which was in Dotty but was removed. So currently Dotty is not shipped on Maven. It means that linker needs itself to be compiled against specific version of Dotty. I would say that this project is not yet ready to be actually used by people that don't want to play around it. First, the Dotty should be more or less used and stable, because this linker actually exercises Dotty a lot. So the branch that I'm showing here now actually has a lot of fixes to serialization of tasty and all that stuff that need to be ported to Dotty back. Yeah, so currently it's not shipped anywhere, and just to make sure that nobody is able to harm themselves by using it.
Is it possible to statically link the Java library into your program?
So for analysis, I'm actually using Tasty. If we'll have some tool or library which is able to get Tasty out of either Java as language or Java bytecode, both seem possible but could be pretty hard, then it would be possible to optimize against Java libraries. But once again, it means that you'll have some non-trivial things for the Java world, because in Java world people are actually used to replace the jars and the class paths more than Scala, I guess. Okay, thank you for the questions.